Inverse relations. So what an inverse relation does is basically returns the dependence back to the independence. So let's have a look at this one. I've got two sets here. So the set A went via some function to the set B. So x went to y. So in this case, it could be the function y equals x squared, for instance. That would do that. Minus 2 would go to 4 and so on. Well, if I want to get it back to another set C, which now you'll notice that set A and set C are equal sets, then I have to apply another function or relation. And so that's y equals plus or minus root x. Would get it back to where we started from. So A and C end up being equal sets when you apply the inverse. Now I suppose that idea is the same for all of mathematics really. Like if you multiply a number by something, then to get it back to the original number you would divide, because division is the inverse operation to multiplication. If I wanted to add, then I would subtract to get it back. And so all those mathematical operations and functions and relations are no different. Have an inverse that will get you back to where you started from. If you want to work out what the relation is, basically you just swap the variables around. So I had y equals x squared. So to work out that inverse relation, if I swap the x and the y's around, I get x equals y squared. But I make y the subject, and that's when I end up with y equals plus or minus the square root of x. So that's how I can find out what relation I would have to substitute into to get back to where I started from. So the domain of the relation then would become the range of the inverse relation, and vice versa. The range of the original one would become the domain of the inverse. Okay? And if you were to draw both on a number plane, there would be symmetry there, but it's in the line y equals x. So if you turned your head 45 degrees, you go, oh yeah, look at that. It's nice and symmetric. So let's try and draw this one. If this is the original relation, what would the inverse relation look like? Well, I'll draw in y equals x, and then I just basically pick some important points. Now obviously any point that's already on the line y equals x, well that will stay there. But any other point, like this x-intercept, I go at 90 degrees to y equals x, and then just measure the same amount. So the x-intercept, you'll notice, became the y-intercept, because all that information is swapping over. So the other x-intercept, that became the y-intercept, and that x-intercept became that y-intercept up there. Y-intercept, if I translate that through, that becomes an x-intercept. Now these turning points are probably good ones to swap over. Ooh, there we go. So each time I'm just going at 90 degrees and then measuring how far apart it is. And I'll just pick as many points as I need till I get a feel for the graph, and ooh, voila, draw it in. And as I say, if you turn your head 45 degrees, you'll see it's got symmetry. So they were inverse relations. So what is an inverse function then? Well, if there is a one-to-one relationship, we already know for it to be a function that for every x value there has to be at most one y value. Well, the reverse has to be true if the inverse is going to be a function. So that y equals plus or minus x was no good, because we could get two possible answers. Now, if it does turn out to be a function, so let me put it another way. First of all, you find the inverse relation. If it turns out that that relation, that new inverse relation, satisfies the rules for a function, then we call it an inverse function. Otherwise, it's just an inverse relation. How do you test? Well, I can look at the original one, and I know that if I use a vertical line test, I can see if it is a function. To see whether it has an inverse function, then I could use a horizontal line test, because we're swapping the x and the y's around. So if it satisfies both, then we know, because it has to be a function to start off with, and then its inverse relation has to be a function as well. So it has to satisfy both the vertical and the horizontal line test. The other way then is to just, as I did before, swap the x and the y's around, If you get an answer that's unique, then it's going to be an inverse function. So there's our parabola y equals x squared. Yes, satisfies a vertical line test, so it is a function, but no, it doesn't satisfy a horizontal line test. So it will have an inverse relation, not an inverse function. X equals y squared. I end up with y equals plus or minus root x. So no, it's not unique, so it can't be an inverse function. As opposed to, say, our cubic over there. Vertical line test, yes, it satisfies. Horizontal line test, yes, it satisfies. So its inverse relation will be an inverse function. And as far as seeing whether it's unique or not, so x equals y cubed, swap the x and the y's around, but make y the subject, I would end up with y equals the cube root of x. And that's unique, because you only have one cube root. Unlike the square root, where we had two, you only get one cube root. So yes, that was a unique answer. That's all for today.